Welcome back, everybody. Especially everybody playing along at home on the live stream. What was that?
I'm trying to be like them at home.
Oh, got it.
But no one has public keys coming out.
All right, so let's talk about where we were and where we're headed, right? We had sections 5.1 to 5.3, and it was all about solving systems of equations. Now, we learned 3 methods of solving systems of equations, right? I guess first off, we should talk about this. What is a system of equations? Well, a system of equations is just 2 lines. Can anybody tell me what the solution of a system of equations is? Like if I'm looking at the lines, where is the solution? When they cross, right? If the solution of the system is where 2 lines will cross, right? So if I've got a graph and I have this blue line and then I've got this red line coming here, the solution to the system is the coordinate. That is the solution. All right? Now, back in sections 5.1 to 5.3, we talked about how we find that point. Section 5.1, we talked about graphing. We can graph to find that point. We use Desmos to graph, right? But we also graph by hand. So we can graph to find that point. Section 5.2, that was our good friend substitution. The one where if you've got a y equals or an x equals, you can plug it in to find the other one, right? Most of us didn't like substitution. A lot of us liked section 5.3, which was elimination. I'll tell you this, from here on, I'm only ever going to let you choose. Okay, you can always just choose whichever one you want to do. The problem is some are set up for substitution, some are set up for elimination. You know, you can choose which route to take, but it might be a little bit easier from one method to the other. So this is where we were at before break. Okay, we did sections 5.1 and 5.2 and 5.3. What we're going to talk about today is solving special kinds of systems. Because let me ask you this. The solution to a system is where the lines will cross. Do lines cross all the time? No. Are there examples of 2 lines that do not cross? Yeah, what are those lines called? Parallel lines. So what we're going to look at today is within those methods of solving systems of equations, what happens when the lines are parallel? What does it look like when the lines are parallel? And also, what does it look like when the lines lie right on top of one another? Those lines are called coinciding lines. Okay? What do 2 lines do when it rains? They coincide. They coincide.
Oh,
That's hilarious.
you just carried my top tier comedy.
Did you guys hear about the
Brown?
no, well, that's funny too. Did you guys hear about the Lego store? Yeah, there was a lot of people there. They were all lined up for blocks.
That's fine.
I don't get it. This is not
Lego store
Legos
lined
are
up
made
for
of
blocks.
yeah, like they're trying to get Lego blocks.
Like Stephen
Yeah, and they were
Block.
lined up for blocks.
Because it was so busy. And blocks, like Lego
Like
blocks.
Stephen
I don't
Block.
know about that.
That was like blocks.
You said like just shut up the jokes.
I got it. It landed. Okay. All right. So there are some times where you could have no solutions, but there are some times where you could have what are called infinitely many solutions. Remember that when we have a no solution, we could use this symbol, right? When we have infinitely many solutions, I am okay if we use the all real numbers symbol. You know, if I was going to get technical about it, because I'm asking where the 2 lines will cross, what points do they share? I mean, we should really do this, because that means any number with any number. But really, honestly, I'm okay if we just write those 2 symbols. Now, don't lose sight of the fact that could the lines just cross once? Of course, that happens. That happens a lot more often than if they are parallel or are coinciding. Okay, so if you get a solution, oh, great. That just means it crosses once. If you get no solutions, that means that the slopes are the same because the lines are parallel. Remember back to chapter 4. For two lines to be parallel, they must have the same slope. Same slope, but also different y-intercepts. Because if they have the same y-intercept, they have the same slope, same y-intercept, that basically means that they're the same line. The equations are actually end up being the exact same thing. When you graph them, you will not see a difference between those two lines. All right, so what we're going to do right now is look at, so what does that mean in terms of those three solution methods, right? Those three methods of solving systems. What does it mean in terms of, you want to come in, Mr. Spavison? No? Okay, cool. He was sneaking through the door. I thought. They're sneaking through the window. I thought he was going to come say hi. All right, so let's talk about graphing. Let's talk about graphing. We're going to use our three methods here. Y equals 2x plus 1 and y equals 2x minus 5. Obviously, I've got these both what set equals to y, and I've got a graph there for you. Let's use graphing. So let's graph these two lines together. I'm going to put the first line in blue. What's the slope of my top line? 2. What's my y-intercept? 1. Remember, slope is 2, which means it's a 2 over 1, right? Okay, y-intercept of 1. That means I go to 1 on the y-axis and I plot my point. And then I use my slope of 2. Rise 2, run 1, right? Rise 2, run 1. Up 2, right 1. Keep it going. Up 2, right 1. Up 2, right 1. Why do I know I'm going up right? Slope is positive. Right? Up right is positive. Or I could go down left because negative negative is a positive as well. Negative divided by a negative is a positive. Negative negative, positive. And so forth. There's my blue line. There's my top line. Let's look at the red line. Y equals 2x minus 5. Well, what do you notice about the slope of the red line? It's 2 as well. We could write it as 2 over 1 if we'd like to. What's the y-intercept? Negative 5. So the slopes are the same, but the y-intercepts are not the same. All right. Y-intercept of negative 5, slope of 2. Rise 2, run 1. Rise 2, run 1. Rise 2, run 1. And so on and so forth. And I can stop here because look at what I see about my lines. The lines are parallel. And if the lines are parallel, are there any solutions? No, there are no solutions. So I say this. Okay. Let's take a look at B. Yes, sir.
So if the slopes are the same, it will always be no solution, right?
Nope. Because what would have happened if I would have done this? Thank you for asking. What would have happened if I would have done this? Are the slopes still the same?
Yeah, but the line's the same.
But the line's the same. So these lines are called coinciding lines. If I were to graph both of these now, they would both have that y-intercept of negative 5. You would not see a difference between the red and the blue. Right. We would not see any difference. So you may be saying, well, why, they're the same line then. They're different lines. They just have the same slope and y-intercepts. Okay? They're different lines. They just have the same, they're in the same location. Okay? All right. So let's talk about this. Now, what method do you think I'm going to use here? Elimination. I would use elimination. Now, could I use substitution? In this case, yeah. Solve for y on the top, just add over the 2x if I really want to. But in my opinion, I think it might be easier to use elimination. The reason why I say that is because everything is lined up, right? Look at my x's, look at my y's, look at my constants. Everything is lined up nicely. Now, is it set up for elimination yet? No. I have to do something to really get it set up for elimination. So let's do that. What do I need to do to get this set up for elimination? Right.
Just times -2?
Right, and I'm glad we said -2. I'm glad we said -2 because you don't want the numbers to actually be the exact same. You want them to be opposites. You want one to be positive and one to be negative. So let's multiply through by a -2 on the top. So that's going to get me a positive 4x, a negative 2y, and a negative 6. The bottom is a negative 4x, a positive 2y, and a positive 6. Now, let me ask you, what happens on the left side? Like if I take 4x plus a negative 4x, if I take a negative 2y and a positive 2y, so what is left on the left side? What remains on the left side? A 0. Hold on a sec, though. What's on the right side?
0.
Negative 6 plus 6 is a 0. Now, is this a no solution? No. This is not a no solution. Because let me ask you, is that a true statement or a false statement? That is a true statement. So what I can say then this isn't all real numbers. You might be tempted to say no solutions because you end up getting zeros. No. Let me ask you this. If I change this up just a little bit, okay, let me show you something real quick. If I do this, let's make that a 9. Everybody just watch up here. What if I had made that a 9? Well, in this case then, this would be a 9. And then this would end up being what?
3.
A 3. Is that a true statement?
No.
So therefore, that's when we would say that this would be a no solutions. What does it tell you about the lines if it's a no solutions? The lines are parallel, right? You should know now, since we know what we know about the no solutions are all real numbers, you should know now, once you get the solutions, you can then tell something about the lines. Yeah.
Wait, so how we get this 9 again?
I just made that up. I just said, what if it was a 9? Just to show you. Either no solutions or all real
Don't worry
numbers.
about it, 0.
I'm just showing you the different examples that you could have. Okay, let's take a look at this next one. Y equals negative x plus 3, and 2x plus 2y equals 4. Now, what method do you think I'm going to use here? Substitution, right? Y equals negative x plus 3, and that's why I'm really going to use substitution, because in the top equation I have a y equals. Okay, so here's how we do substitution again. Remember, because I have a y equals, I know I'm going to take that y equals and plug it into the second equation. This negative x plus 3, y is equal to negative x plus 3. That's what goes into the second equation. Where does it go? In place of y. So this gives me a 2x plus 2 times negative x plus 3 is equal to 4. All right, well now we just keep solving. Distribute. So 2x minus 2x plus 6 is 4. What do you notice happens with the x's? They cancel. And that, you're going to see a common theme here. If the variables end up canceling, it's a special case. If they don't end up canceling, it's just one solution. The lines are just going to cross once, like we've had the rest of the time that we've been doing this. If the variables cancel, then it's either no solutions or infinite solutions. Right, so now since we end up with a 6 equals 4, something that's a false statement, we would say that would mean there are no solutions. So somebody asked me at the end of last period, so what do we write in the answer blank? 6 equals 4? No. We don't write 6 equals 4.
No,
You answered that really
no, Mr. Roderick, I swear I did it before you even
We don't write the answer blank as 6 equals 4. We write in the answer blank no solutions, because that's the end goal of this. That's the end game. What are the solutions? There are no solutions. Okay, let's take a look at this next one.
Poor guy.
What would I do here? Sid?
You do
-2 on the top again? Yeah, same type of thing. Yeah.
I was gonna just say like, or elimination.
Elimination, right. And to eliminate, I'm going to multiply by -2 on the top again. Shh. Let's distribute in that -2. Top equation becomes -2x, -2y, -6. Bottom equation, 2x plus 2y equals 6. And what happens again? Everything cancels. The left side all cancels to be a 0. The right side all cancels to be a 0. So therefore, what are my solutions? Infinite solutions. Say that again. Infinite solutions. Now, what does that tell me about my lines then? If I say that these lines are they're infinite solutions, what does that tell me about my lines?
They go off the page.
The thing that looks like this, right? You can't see the difference. The coinciding lines, right? The ones that the raining ones, right? What do they do when it rains? They coincide.
No, that's not something I love. Sounded better in my head.
Questions about that? So, moral of the story here is, if the variables cancel out, it's a special case. You have two options if the variables cancel out. You can say no solutions or infinite solutions. If you solve the equation and it gets you something true, like this one, it's an infinite solutions. If you solve the equation and it gets you something false, that would be a no solutions. Now, what happens if the variables don't cancel? It's the exact same thing that we had been doing before. That's when the lines end up crossing once, if the variables don't cancel.
Perpendicular.
It could be perpendicular, but it doesn't necessarily make it perpendicular. We just know that it's going to cross once. Okay? And that's pretty much every single problem that we had done before today. The lines end up just crossing just once.
So that's when it's actually like x equals something.
Right, you get x equals y equals, you get a coordinate on the blank. Yeah, the whole deal there. We're just talking today about what happens when something weird happens. What happens when the variables cancel out? That's what we're looking at. Okay. All right, that's all we got for today. I'm going to shut off the video.
Can we throw away everything in the first quarter? The first quarter.
First quarter.